Good morning and welcome. Thank you for joining us for another edition of New England Chapter Connects. My name is Regina Hackett. I'm the Communications Coordinator for the Connecticut T2 Center, a member of APWA's New England Chapter's Public Works Awareness Committee, and the producer of today's webinar. Our topic for today is increasing efficiency in winter maintenance, weather versus road weather. In exploring the relationship between air and road temperatures, we can start to uncover answers to an important question. To what extent do road temperatures differ over short distances? Understanding these variances is crucial for efficient and effective winter maintenance operations. Our discussion will pivot around the contrast between standard atmospheric weather conditions and those that are specific to roads. We'll shed light on the extent of these variations, the factors contributing to them, and why this knowledge is indispensable for winter road maintenance strategies. This discussion aims to uncover the value of understanding road temperature variations and bolstering winter maintenance operations. And just a couple of things before we officially get started. Special thanks to our APWA New England chapter sponsors. Without the support of our sponsors, we could not bring all of the valuable programs and events to our members in the public works community. Our chapter events are made possible because of the generous support of our sponsors. Their continued support of the chapter is so very important. Thank you, chapter sponsors. We hope that you will find the New England Chapter Connect series worthwhile, informative, and a way to stay connected. This is our first session of the fall series. Upcoming webinars will be held on October 24th and November 12th. Registration information and a promotion for those webinars will be coming in the next couple of weeks. If you missed a session or would like to replay a session for your staff, all of the New England Chapter Connects webinars can be found on the New England Chapter website. Lastly, if you're not an APW member and would like to be, or would like more information on upcoming New England Chapter Connect sessions, or if you are interested in becoming a sponsor, all the information can be found on the chapter website at newenglandapwa.org. And now let's get started. I'm pleased to introduce today's presenter, Eric Faulkner. Eric is a meteorologist and weather advisor for Vaisala X-Weather. He has a degree in meteorology from the Ohio State University. For 13 years, Eric has been helping businesses in a variety of industries to better manage the risk weather poses to their operations, including energy trading, agriculture, oil and gas, renewable energy, utilities, transportation, and government. Most recently, he has been assisting winter maintenance professionals with weather and road weather education and is advocating the use of new technology to increase efficiency. Eric is originally from Pittsburgh, Pennsylvania, but has also lived in Columbus, Ohio, and Rockville, Maryland. He currently resides in Charleston, South Carolina, where he has been for the last 8 years. Welcome, Eric.
Thank you, Regina, and thank you, Tom. Thank you to the New England APWA chapter for having me on this session today. I will go ahead and share my screen. Okay, can you see the screen okay?
Looks good.
Perfect. So as Regina mentioned in the intro, today I'm going to be talking to you all about weather versus road weather and really the importance of collecting road weather data. Before I get into that, I want to just give you a little bit of background on the company I work for. So some of you may be familiar with Vaisala X-Weather, some of you may not be. Vaisala is a very large company. It is global in nature, as you can see from this graphic here. We have offices spread from North America to Europe to Asia, with our headquarters being in Helsinki, Finland. So we do have several offices, though, here in the U.S., one of them in the Northeast being in Boston, but our headquarters in the U.S. is in Boulder, Colorado. Vaisala has been in business since the 1930s, so almost 100 years. So it's been around for quite some time, and we're hoping it continues to be around for much longer than that. Vaisala started with the image on your screen. So there was a guy named Vilho Vaisala, and he was the first one to introduce the weather balloon / radio sonde in Finland. So these are the things that we launched thousands of per day now. And what they do is they go up into the atmosphere and they're able to collect weather data at different levels of the atmosphere. And we use all this information to then produce weather forecasts, the weather models that you might see on your local news station or from NWS, even the models that go into your traditional weather apps that you have on your phones. So this data is imperative in understanding the atmosphere, what's happening to then produce a weather forecast. So Vaisala was one of the first ones to start this and was the first one in Finland to launch one of these balloons. So pretty cool. We also have some really great technology. Vaisala is known for weather sensors. That's how the company first started. We have plenty of weather sensors today, though we're moving more toward a software approach recently. But we have weather sensors protecting the Mona Lisa, for example. We have a temperature sensor and a humidity sensor on the Mona Lisa to make sure the levels are correct. Because if they're not, then the painting could deteriorate much more quickly, and we obviously don't want that to happen. We've also put sensors on the Mars rover, including temperature, pressure, humidity, all kinds of different things to get some indication on the conditions that are found on Mars. So our weather sensors really are everywhere. They do a number of different things. They're based on a number of different applications. And then we also, and where I work, have weather sensors for roads too. So as Regina said, I am a meteorologist and weather advisor. I'm primarily on the road weather team, helping city governments with their winter weather operations. As she mentioned, I'm originally from Pittsburgh, Pennsylvania. I grew up there. I spent a majority of my life there. 8 years ago, I moved down to Charleston, South Carolina, which is ironic because I work primarily in winter weather and I live in a southeastern coastal city that doesn't see much snow. But obviously, I'm used to it being from Pittsburgh, and I will tell you, when it does snow down here, if you've ever heard that the South just waits until it melts, that's absolutely true. That's all we do. We don't have any infrastructure whatsoever. So when it does snow here, we hope it warms up quickly so that it melts so that we can get back on the roadways. I did get my degree in meteorology from the Ohio State University. So apologies if there's any Michigan fans on the call. I'm a big Ohio State fan, so much so that I named my golden retriever Buckeye. So he has the benefits of having a dog dad that is a huge Ohio State fan. All right, so let's get into the meat of the presentation here. So it's all about traditional weather versus road weather. When you think about traditional weather, really what it is it's the weather around you that's happening in the air. And this is traditionally meant for the general public. It's meant for consumers. So a typical weather map that you might see is on the left-hand side, where you have the different colorations based on air temperature. You have your barbs based on the wind speed and wind direction. And then on the right-hand side, that's just general weather that's happening, right? It's snowing. It's probably cold outside. The visibility is low because the snow is heavy. And that is all information that you can really see with your eyes or get through any type of weather service. What I'm going to really focus on a little bit more is road weather. So road weather is focused on what is happening on the road surface. So while the general public cares about traditional weather, the public works officials and snow fighters really care about what's happening on the road surface. What you guys do. Now you also obviously care about what's happening in the air too, but this is even more important because you're actually treating the roadways during a winter weather event. So what you could get from road information is road temperature. You can get an idea of the condition of the road, what the friction on the surface is, even the amount of salt that's on the roadway. And a good example of this is the image to the left, where you see the roads going underneath the overpass. They look fairly clear, fairly wet, but the overpass is snow covered and looks fairly hazardous, likely because that temperature of that overpass is probably a lot lower than the roads going underneath it. So this is a good example I like to use, and it's just an AI generated image. But let's assume this is a coastal town somewhere in the Northeast. You can see the water there at the bottom. and then the neighborhood up to the top. With a standard weather forecast, what you're likely going to get is they're going to tell you that the air temperature is 32 degrees over this entire area. Now, closer to the water, it could be 35 degrees. Back further away from the water, it could be 31 degrees, but essentially you're going to get an average over that area, and they're going to say the air temperature is 32 degrees. Now, you can take this even a step further when you talk about the roadways too. So this roadway over here could be 34 degrees, but this roadway here could be 29 degrees. And that's a significant difference. If there's a road that's a few degrees above freezing, any snowfall that does fall is going to melt on contact. But if you have a road surface temperature that is several degrees below freezing, it likely needs attention. So looking at the information this way can help you divert resources to certain areas that need it and not focus on other areas that don't. This was an example, and I'm going to leave the sound off in the video, but I was at an APWA conference in Syracuse, New York. And at the time, I think it was March, and at the time you can see it's snowing heavily. The snow is sticking on the grass, it's sticking on the cars, it's sticking on myself, and the visibility is pretty low as well. I would say the snow is probably about an inch per hour, roughly, in this shot. But you can see the pavement's just wet. The reason being is because the pavement temperatures in that area were about 38 to 40 degrees. So the snow was falling heavily. It was cold as far as the air temperature was concerned. It was close to freezing, but the road temperatures were far more elevated and there was no accumulation on the road surface. So if you would just look out your window and say, oh, wow, it's snowing very heavily, we need to go get out there and treat the roads. In this scenario, you would potentially be unnecessarily spreading treatment during a time when it really doesn't need to be spread. So that video is just a very good example, a real world example of what could happen based on the difference between weather that's happening around you and what's actually happening on the road surface. So what affects road conditions? Well, there's probably hundreds of things that can affect road conditions, honestly. These are some of the main ones here. You've got your atmospheric weather, so that's your standard weather, your traffic, solar radiation, topography, urban heat islands, artificial structures, large bodies of water, and shading. So all these different things can affect road conditions. Excuse me. And what the general weather models do is they try to factor in a lot of this when they're producing those weather forecasts. So I talked about the weather balloons earlier. They're ingesting that information for the weather models. The weather models are also taking this information into effect to a certain extent. So they take atmospheric weather, they've got your solar radiation, they do attempt to take topography, urban heat islands into effect, and large bodies of water, that they're not as good at that. They're getting better. But a few of the things that they don't take into effect, and I forgot to mention one before, is the traffic. They don't take into effect maintenance activities, artificial structures, or shading. None of that really goes into your major weather models to produce a weather forecast. So those are key pieces missing when we're talking about standard weather versus a road weather forecast. Okay, Regina, if you want to queue up poll number 1. So in this poll, I'm curious to see what you guys think about how much road temperatures can actually vary, or how much they can actually vary on a network. You got 3 different choices there. You have 10 degrees, you have 20 degrees, or you have 30 degrees. And this is coming from our experience. So we have plenty of road sensors out there. We have for a long, long time. We have a new network that we've been building out. So we have a lot of examples of the differences that we could see on the temperatures in any given road network or road networks across the US. So if you want to please vote in the poll, I'd be curious to see the results about how much you guys think road temperature can vary on a single network. And then I will reveal the answer and give you an example with it as well. And Regina, I didn't ask you, but okay, there are the results. Wasn't sure if I'd see them. Okay, so the results on how much road temperatures can vary. So 10 degrees Fahrenheit got 32% of the vote, 20 degrees Fahrenheit got 56% of the vote, and 30 degrees Fahrenheit got 12% of the vote. It's really going to depend. So this isn't a finite answer because all road networks are different. And like I just said in the last slide, there's so many different conditions or variables that can affect the conditions on a road network. However, the answer is 30 degrees plus. That's what we've seen on road networks in our sensor network. So I've seen an instance where there was a time, and this was during summer, so shading was likely playing a role here too. But there were a couple of road sensors 3 blocks from each other. The one road sensor was reporting a temperature of about 105 degrees, and the other one 3 blocks away was at 76 degrees. So that was about a 30-degree difference in that example right there. And we've seen higher differences on road networks. Again, it's going to depend on the size of the network. It's going to depend on topography, geography, shading, all these different things. But we've seen them as much as 30 plus degrees. So a good example of this, and this is during the winter when it's more important to understand the road temperature, is from actually kind of close to the area that I was in that video. It's just north of Syracuse or northwest of Syracuse, New York. I want to say this was in January. I can't remember the exact month, but I think it was in January where there was some lake effect snow coming off of Lake Ontario there. And these 4 dots that you see are road sensors in the area, and the temperatures are the road temperatures. So you can see how much they actually vary between the 4 locations. And these 4 locations aren't that far apart from each other. They're probably about 5 to 10 miles, depending on which location you route from the other. So the one really interesting thing is these 2 in the middle, right? So you have the one just north of Fulton here that was 31.5 degrees, and then you have the one just south of Fulton that was 41.4 degrees. So that's a 10-degree difference in road temperature just across this very small distance. And this is during the winter. This isn't during the summer. This isn't nothing to do with shading. That's a 10-degree difference right there. And yes, for the one that's 31.5 degrees, there is precipitation. There is snow falling in the area, so you likely have some cooling on the road because of that. But that's still a major difference, 10 degrees there between those 2 sensors. So what you could do with this information is you could say, okay, well, we've got a lake effect snowband coming in. We've got this one sensor up here that's 31.5 degrees. We've got another one over to the west that's almost 35 degrees. Right now, we should probably devote our resources to the area that's below freezing on the roadway to make sure that those roads are in good condition, apply some treatment there. And then after that, we can redirect and maybe go to the other locations depending on the road temperatures at that time. So again, it's all about just more efficiency in planning, rerouting if necessary, targeting certain areas based on the information that you can actually collect. So this is a really cool example. Move this over from earlier this year. So I wanted to include this because we don't experience total solar eclipse very often. So this is my crude illustration of the path of totality. So this was back in April. And all the green dots that you see on the screen are locations of sensors, road sensors in our new network that we had just launched a couple of years ago. So you see the path of totality goes across some of those locations where there are road sensors in the roadways. And I wanted to highlight certain areas to show you how much the temperature dropped in these locations during the total solar eclipse. So down here in Texas, we had an average drop amongst the sensors in the area of about 20 degrees. This is road temperature of about 20 degrees Fahrenheit with a max of 26. Southwest Ohio, we saw about a 20.5-degree drop with a max of 25. Northeast Ohio, about 20 with a max of 21. At New York, we had an average of about 14-degree drop with a max of about 19. And then up in Vermont, we saw the largest drops with an average of about 23 and a max of almost 26 degree Fahrenheit drop. And in this graphic, you'll notice that the New York section is a little bit lower as far as the temperature drops are concerned. The reason being is because there was cloud cover in the area during the day of the total solar eclipse. So that pavement didn't heat up as much as the other areas because there wasn't that solar radiation to really warm it up. So the road temperatures were starting at a low point, which is why the drop was a little bit lower. In Vermont, where we saw the greatest drops, it was clear blue skies during the event. Right before the total solar eclipse started to happen, we had a road temperature at this location of 93.2 degrees and ultimately bottomed out in a few hours at 67.6 degrees. So that's a massive drop within a few hours. And I'm not saying that, obviously we don't experience total solar eclipses often, and that's not something that's going to factor into your winter maintenance plans. I'm just showing this example, one, because it's kind of cool because it happened this year, and two, because it can show you how much road temperatures can really change given the correct conditions. So even in my area in Charleston, we were only about 70% solar eclipse, so we weren't even close to the path of totality. And I've got one of these sensors in my backyard, and the surface temperature went from 119 degrees down to 96 degrees, and the air temperature even dropped from 74 degrees down to 69 degrees. So 70% total solar, or 70% eclipse here, and there were still significant drops in both road temperature and air temperature. And you can obviously notice the difference between the two. There's a much more significant drop in road temperature than there was in air temperature. Okay, so let's talk about some of the challenges. Obviously, there are challenges with your standard weather forecast. There's just not enough information there. Yes, it's good information for what it is, but ultimately, more is really needed. So looking at the graphic to the right-hand side, you may have some weather stations around your community or your road network. We work with a lot of the DOTs, have for 30 years, and they have different networks of ours where they can collect road weather data. You might be able to pull some of that information from them, and that's great if you can. That's another data source. But going through all the examples I just went through, that roadway that's the DOT's roadway, the state highway that they maintain, is likely going to have a different temperature than your roadway based on the variability. And again, the idea is to fill in these data gaps where there isn't any data to get information coming directly from your road network so that you have real-time data custom to your roads, and then you have a localized forecast custom to your roads. So that's really the idea. Fill in the data gaps, get some more road weather forecasts, and produce a better, more accurate road weather data to produce a better, more accurate forecast. Okay, so what challenges do you guys face during the winter season? There's probably a million of them. I've listed several on here that typically we hear from our customers, from the communities before, during, and after the winter season of what they dealt with. One big one right here in the middle, I'm not going to go through all of these, but one big one right here in the middle is lack of communication. So many times I hear, well, the public works director is using this app, and then the highway superintendent is using a different app, and then the drivers are using a third app, fourth app, a fifth app. So they're all using different weather information to try to make a cohesive, consolidated decision. And you can imagine how difficult that probably is. So the lack of communication is one thing that's a struggle because it's not a consolidated approach. There's all different kinds of information. All these weather apps are going to be different in what they say. So if you're not using a singular method to make those decisions, then it's going to be a struggle when a winter weather event happens. A couple of others are down here at the bottom that I hear all the time too, unnecessary call outs or quote unquote sit and wait. So snow is expected in the forecast, maybe it's expected at 5 p.m. Call in the crew and snow doesn't start falling. It's 5 p.m., turns to 6, turns to 7, turns to 8, still not falling. So the timing of the forecast was just not great, or something happened where the storm didn't act like they thought it was going to. So at that point, if they're sitting and waiting, and I understand, drivers like the overtime, they want to get paid. I completely get that. But if they're sitting and waiting, then it's costing you money on labor. If they're called out and they're actually driving around and they're spreading salt when they don't need to, it's costing you on material, it's costing you in gas, it's wear and tear of vehicles. So all of these risks and issues could be mitigated just with having more clarity and more understanding of what's going on the road network. So those are a couple of the bigger ones. There's one at the bottom here too, work-life balance, which is very difficult for a snow fighter to have. If there's a big storm coming, there's nothing you can do about it, right? You have to go out to clear the roadways. You have to make sure the community is still safe and active as much as possible. However, some communities I've spoken with, they want to try to increase the work-life balance as much as they possibly can. So if there is an instance where they're calling for snow, right? Local news says 2 to 4 inches of snow, but the pavement temperatures are going to be in the mid 30s or upper 30s the entire time. Maybe you can avoid a call out. Maybe the guys can know ahead of time so that they can go and then plan their personal lives accordingly. Maybe it's during a holiday and they want to spend time with family and they don't want to have to be in if they don't need to. That type of thing is what the benefit is in increasing the work-life balance. Like I said, it's not possible to do it 100% of the time, but when it is possible. Okay, so I put a few scenarios together so that I can show this to you in practice and how it would work as far as decision making. So we'll just call them scenario 1 and scenario 2. So say in scenario 1, there's an air temperature of 31 degrees, heavy snow at about 1 inch per hour. Same thing with scenario 2. You have an air temperature of 31 degrees, heavy snow at about 1 inch per hour. So you have the same data sets in both scenarios. Would you make a different decision? I mean, in this case, likely not. You've got the same data, air temperature 31, heavy snow 1 inch per hour. If that's all you had, you're likely out there treating, out there plowing if necessary. Let's add a data point to these scenarios. So scenario 1, your road temperature is 29 degrees. And scenario 2, you know that your road temperature is 36 degrees. So in scenario 1, you're probably going to make the same decision that you would before knowing the road temperature. Now you know the road temperature, so you're definitely going to be out there treating or plowing, depending on how much snow is on the road. But in scenario 2, now you have an opportunity to potentially make a different decision. Yes, the air temperature is below freezing. Yes, there's heavy snow at 1 inch per hour, but the road temperature is 36 degrees. So any of that snow is going to likely be melting for the most part on impact on that roadway. So then you can determine what to do from there. Maybe you still go out and treat, I don't know. But at the same time, you now have that data to make a different decision if you want to. We can take it even a step further. So scenario 1, the forecast calls for the road temperature to drop even further to 26 degrees with only 5 pounds per lane mile of residual salt left on the road. So again, at this point, you're going to be out there. You're going to be treating, you're going to be retreating, potentially plowing at this point with heavy snow over the past 3 hours. In scenario 2, we are expecting a drop of road temperature closer to freezing, down to 33 degrees. But we still have residual salt of about 50 pounds per lane mile on that roadway. So with the temperature drop and with heavy snow, you might go out and treat at this point, but with some of the residual salt left over, maybe it was from the previous storm, maybe you had pre-treated, you know that there is still salt left on the roadway, and maybe it's a lighter treatment that you can go out and apply and not just dump as much salt as possible. So again, we can go round and round in circles on this with the data to make different decisions. But really the key here is having the information to be able to then make these different decisions that you would make without having that type of information. Okay, Regina, can you pull up pull up poll number 2? And poll number 2 is going to ask you how you are making decisions right now. It's only going to give you a few options. And then I think it's all of the above or other. So if you could vote in poll number 2, I'm curious to see how you guys, what resources you're using to make decisions. And then we're going to go through all of the different options available and which ones are better, could be better than others. So I think I saw the poll pop up.
We still have people voting. Hold on.
Okay. I had it pop up on my screen and then I had to minimize it because I accidentally clicked too far. Okay, here we go. So what is your main source of information? So just your eyes, which got 0%. Police department, 0%. Local news free weather apps, 15%. It was kind of a tricky poll because then I had all of the above, which was 76%. So all the above, eyes, police department, local news, free weather apps, 76%. And then other was 9%. So it is very interesting. Most of you are using eyes, police department, local weather, and then only 9% are using other methods. So there's a number of different ways where you can make decisions. The first 3 were the 3 that were listed on there. So you've got, yeah, your just general understanding. Look out the window. Is it snowing? Do we need to go out? Yes or no? If you have a resident complaint or the police department calls you in and says, hey, snow is starting to stick on the roads, you guys might want to get out here and do something about it. Free weather apps are obviously popular. NWS and local news are freely available information that you could just get. So that's a no-brainer to use those. The other was 9%. So other might have been one of these next 5. Paid weather solution, there's several of those out there. You can get a paid weather solution anywhere. Most of them are probably not going to have road info. If they do, there's not going to be any local observations that are really backing that road information for the most part. Some of them do. Cameras are another thing. Some communities will have traffic cameras already in place. Some other road weather providers will offer cameras so that you can visually see what's happening on the roadways. You've got your handheld thermometers, and I'm sure many of you probably have, where you physically go out, you point it at the pavement, you get the pavement temperature with that. Some will have vehicle thermometers, which are mobile, which you mount on the vehicles, which you can get the road temperature and air temperature. And then finally, road sensors are the last one on here. So Regina, if you could pull up poll number 3, this question is just going to be focused on road sensors. And based on the last response, I'm assuming many of you probably are not utilizing road sensors, but I want to know what percentage of the attendees on this call right now are actually using road weather sensors to make their decisions for their winter maintenance operations. And as you guys vote on that, I want to say to you, none of these are wrong. None of these are wrong ways to do things. They're all kind of good in coordination with each other. You probably should have some of all of these in reality. But I will say, okay, so it's actually higher than I thought. We got the poll results. Do you use road weather sensors? Yes, 38%, no, 62%. So 38% of you are actually taking advantage of road weather sensors. And I guess that could be on your network or from DOT sensors around. But road sensors really are one of the most important things when it comes to winter maintenance operations because you're getting data directly from your road. They're very accurate. You're getting data right there. You're getting consistent data coming in so that you can understand how things are changing and evolving. And then you're also potentially, depending on kind of what you use, you could get an enhanced, more accurate forecast on those road sensors. And I'll talk about that in a little bit. But what they also allow you to do is they allow you to be proactive as possible. Again, not saying any of these other things are wrong, or not saying these other things don't allow you to be proactive in some respect, but road sensors really allow you to be as proactive as possible. The first key to that, you have greater visibility on your road network. So if you have road sensors placed on your road network, you can see what's happening on your road network without driving around to figure it out. The second thing is you're able to reduce your costs. Maybe you don't have a call out because of the information you're seeing. You don't have people driving around waiting for something to happen. You're reducing your cost in your labor, your fuel, your maintenance, and your material potentially as well through targeting. You're also reducing environmental impacts through less material usage. This is becoming more and more important. Obviously, salt getting in the waterways is increasing salinity, and that's not the best for ecosystems typically. So at some points, you're going to have to throw as much salt in the storm as you need to. You have big nor'easter coming in, and they're calling for 2 feet of snow. You're going to just have to do what you got to do. But there are a lot of these storms, especially right on the coast where things tend to mix with rain and stuff like that, where you could maybe maneuver some things around, maybe spread less salt to reduce that salt impact on the environment. Salt's also corrosive too. It's corrosive to the roadway, it's corrosive to property. The less salt you throw down, the more money you potentially could save in the long run to prevent your roads from corroding or deteriorating as quickly and then having to pump more money in them to fix them with paving operations. And then the most important thing for all of you, and the most important thing we want to see to you, is keeping your communities safe and active. So if you err on the side of caution, that's absolutely what you want to do, and that's absolutely okay. But there are ways to utilize the data where you can still err on the side of caution, but still also help reduce costs for you guys, ultimately reducing costs for your taxpayers. So how do you become proactive? Well, there's a bunch of different, jumped ahead. There's a bunch of different data that can allow you to do that. This is all different kinds of data that you can see ahead of time to know what's going to happen. Is the road surface wet? What is the surface temperature? And more importantly, how is it expected to change? If it's expected to increase over time, you're going to make a different decision than if it's expected to decrease over time. Dew point temperature, is there residual salt on the road surface, which is nice to see, to then determine how much of an application you need. Is it going to rain or snow? Obviously, that's important. Determining the type of precipitation. Will it begin as liquid is important to understand if you're going to pre-treat ahead of time, especially with brine. And then could the subsurface impact the road surface temperature? So there's a lot of different things that different data sources that you could have that could help you become a little bit more proactive in the approach. So I mentioned that I was going to talk about the forecast and how the data actually powers the forecast. So I call these sensors mini meteorologists because that's really what they are. They're recording information at the site, they're learning the site, they're understanding the site. That's what a meteorologist would do if they're focusing on a particular area or a particular region. And in this image, this is on a pole, and there's a little road sensor at the bottom. So it's not a camera, but I call it a camera type of lens because it's a lens that shines down the pavement to record the pavement temperature. And you can see the shadow of this tree in this image. It's kind of hard to see. It's at the very bottom corner. It's a dead-end road. There's a shadow of a tree here. That's important to the next slide. So what you're looking at here is you're looking at surface temperature, which is the road temperature, air temperature, and dew point temperature from that sensor. So this is the data in real time. And then over here, the dotted line is the forecast. So you can see this weird little, the green line is road temperature. You can see this weird little dip, right? And right around noon. So there's a dip. It increases, dips down, then increases again. So I was thinking, like, what's happening with this sensor? Like, is it broken? Is there something wrong with it? Like, I don't understand why that's happening. Well, that tree that was nearby, as the sun angle changed, the shadow of the tree basically overtook the spot where the road sensor was pointing. So as the shadow of the tree moved over, the shadow cooled down the pavement temperature, which is why you see this dip here. And then as the shadow moved on later in the day, the road temperature would heat back up because the sun was then shining on it again. So that's interesting in itself because it's kind of unique to that specific area. But the more interesting part of this is that the forecast started picking up on this unique differentiation. So the forecast was picking up that, okay, under sunny conditions during this time of day, there is a decrease in road temperature. And then after the decrease, after a certain amount of time, it starts to increase again. So the forecast model doesn't know that it's just shadow. It doesn't know specifically what it is. It just knows and learns what's happening in the area. And it's using AI, artificial intelligence, to do that. It's taking that data that mini meteorologist or sensor is learning in the area. It then learns what happens in the area over time and then produces a better, more accurate forecast. Now, it's still not going to be 100%. I mean, even you can see here, there's a dip, but it's not as big of a dip. But over time, it'll continue to learn and continue to improve upon that forecast in that area. And that's not to say that you're going to have tree shadows impacting these forecasts everywhere, but it's just an example to show you how it works and how much it actually does improve. So we ran some tests and analysis on our network that we have, and this was from Central Ohio. And there are two different options, and if I have sensors, and if I have some time, I'll show you what they both are. But essentially, all you need to know for now is one's pole mounted, one gets mounted into the road surface. And what we did is we co-located these two. So they're pretty close together, I don't know, 100 feet apart, maybe. And we analyzed these over the course of a winter to determine, one, how accurate the data was, and two, how accurate or how they compared with each other. So the orange line is the ground sensor called GroundCast. The yellow line is the pole-mounted one called TempCast. They both do road temperature. And what we found was the improvement of the forecast utilizing that road temperature data from GroundCast improved by as much as 80% in the first few hours. For TempCast, it was less improvement, but still improvement, about 40% improvement in forecast within the first few hours. And if you even extend this all the way out to 36 hours, like this chart does, you can see that GroundCast still improved the forecast by about 40% out to 36 hours, and TempCast still by almost 20% out to 36 hours. So just more analysis and more understanding of how they actually do improve the forecast by ingesting that real-time data. They're learning the areas to then create something that's a bit more accurate. Now, you can also see from here, too, that the GroundCast was more accurate than TempCast, which is also not surprising, given that GroundCast is right on the ground and level with the ground. And TempCast, what it does is it takes an area and averages it out, and it sits higher up on the pavement. So there could be some interference and a number of things here that cause it to be a little bit less accurate than the GroundCast. So this is a good example from a customer of ours in Cranberry Township, Pennsylvania. So they're just north of Pittsburgh. They maintain 132 miles of road. They have 23 operators that are available on staff, 20 trucks with plows, and they use an average of about 4,800 tons of salt per year. So just a little bit of background on that. Now, there was an event back in February 22nd, 2023. This was almost 2 years ago now, but I like to use it because they commented on it extensively, and it is a really good example regarding callouts. So February 22nd, 2023, NWS and local news was calling for freezing rain in their area. There was a winter weather advisory for Butler County, which is where they're located, and they had to prepare accordingly. However, they had a few sensors at the time. They were looking at the forecast data that was coming from the sensors expected for this event. So they saw that at the beginning of the event, the surface temperatures, and this is probably a little hard to see on these slides, but the surface temperature here at the beginning of the event was above freezing, about 34.5 degrees, or was expected to be. Then the surface temperature is this green line here. They could see that throughout the event, the road temperature was going to actually increase. So it wasn't going to get near freezing. There wasn't, according to this, going to be any issues on the roadways outside of wet roadways, even though this was a freezing rain event. So what they do, They were worried about it. Obviously, you don't want to mess with freezing rain. That could cause significant issues on the roadway if you don't do anything about it. But what they said is, you know what, we're going to trust it. We have these sensors in place. Let's trust it. We're not going to call anyone in. We're not going to deploy. We're not going to spread any material. Fast forward to the next morning when the event actually took place. At the beginning, the surface temperature was actually even a little bit warmer, about 36 degrees, and continued to rise throughout the event. So in the Cranberry area, there was freezing rain too. It wasn't like the NWS was wrong. There was freezing rain. There was accumulation of ice on elevated surfaces, on light poles, on trees. But because the road temperatures were above freezing and significantly so, they just remained wet. So in this instance, what happened with Cranberry is every time they don't send people out, they save, for their operation, they save about $10,000 on a call out. So for this example, they saved $10,000 on a call out. They had the decision, they made it ahead of time. So they told their staff and their crew, you guys can sleep, don't worry about it. We're not going to be calling you in tomorrow. I mean, obviously, they probably said if anything changes, we'll let you know, but it didn't. And they were able to sleep through the night without having to worry about, getting up earlier or waiting for that call to come in. They were also able to provide some transparency to the residents because communities around them were dumping a bunch of salt ahead of this event and during this event. And their residents were like, why are they salting the roads and you guys aren't? Well, they said, well, we have this information with the sensors in the system, and this is why we weren't dumping salt. And we actually saved you all money. And then the residents were like, oh, okay, that makes sense. And we're glad that you were able to save us money on this while the roads were only wet. So just a really good example of how one community was able to utilize it to prevent a call out during a winter weather event. There's a couple other examples here, and I know that I'm getting low on time, but this is a frost example. So this is showing how the surface temperature was expected to drop below the dew point, and at that point you have condensation. If the surface temperature is below freezing, you get frost. So it was showing two instances where this was going to happen, January 29th and January 30th. I pulled this information or these images from Twitter, now X, from Chris Kubal. He's a meteorologist out there. This was in the Des Moines, Iowa area, and he verified this. So morning of the 29th, frost on roadways. Morning of the 30th, frost on roadways. So having the information to understand what's going to happen, being proactive, knowing ahead of time, maybe let's apply a light treatment or have, maybe a skeleton crew come in to take care of this to make sure the roads are safe in the morning. One more example for you all. This was from a customer in Missouri, right outside Kansas City, suburb there. They have a projected level of response based on the expected snowfall. So in these examples, they were using their local news or National Weather Service for their forecast. What they were calling for, what VISLA was calling for as far as our sensors and our forecast, and then actual totals. And what they noticed was by using our forecast and utilizing that, they were actually able to save a projected $56,000 through the winter of 22-23. I think they put a table together for us this year too. It was about $80,000. And that's going to fluctuate, obviously, based on the winter season and how many events you get to. But just to give you an indication of how much money could potentially be saved based on the decisions made by utilizing more data. Really quick here, I see Regina, you popped on. So really quick, this is a network just to give you guys a sense of what's out there. So right now, these are the number of sensors in our new IoT network that we have out there that's collecting road weather data. So not every state is utilizing it. We have some states utilizing it more than others and have bigger networks, but just to give you a sense of where it stands. And that's it. So if you do have any questions, I would love to answer them here. The other thing I do want to mention quickly is we created a new YouTube channel too, and I actually provide weather forecast ahead of events on this YouTube channel. So it's free to subscribe. So if you want, feel free to click that link, subscribe to the YouTube channel, and then you'll get weather forecasts ahead of winter weather events during this upcoming season.
Okay, does anyone have any questions today? Oh, I'm trying to copy this the YouTube channel thing down so they can just copy and paste it outside from
Thank you.
the chat box. Okay. All right. Well, Eric, thank you so very much. This was very informative. We really appreciate you coming to speak to us today. And what I'm gonna do, I apologize. Okay. That didn't work out, did it? I'm trying to put the QR code for if everyone can take a moment, please, to fill out an evaluation that we have for today's session. We would really like to hear from you. Are you guys seeing the QR code?
Yes.
Okay, perfect. All right, wonderful. And then okay. Well, again, thank you so much, Eric. We really do appreciate it. We'd love to have you back sometime.
Yeah, thank you, everyone. I really do appreciate you having me.
All right, wonderful. Have a great day.
All right, you too. Bye, everyone.
Bye-bye.